Greetings and welcome, friends. Welcome back. We're taking a look at a brand new zone. We're talking about polynomial functions, polynomial, multi-termed expressions, right? Except this time, they're functions. So it's going to be good. Last chapter, we were looking at quadratic functions. Quadratics are a type of polynomial. But now we're going to look beyond second degree to like third degree, fourth degree, seventh degree, stuff like that. It's going to be good. So the first thing I want to talk about is a polynomial in a single variable. So today we're actually, oddly enough, the name of the zone and the section are similar here, if I might say so. So a polynomial of one variable. Variable. All right, it's going to look something like this. I guess I'll just write it out like this. It'll be a sub 0 x to the n, and then plus a sub 1 x to the n minus 1, and then plus dot 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 plus a sub n minus 2, for instance, times x to the second. Actually, I'll just do x to the first. Plus, then I guess, no, it has to be a 2 now that I've started it that way. And a sub n minus 1 times x to the first plus a sub n.
Wait, so is this stuff going to be on the internet?
Nope.
Okay.
Nope. So basically, what I want to point out here is all of these a terms, the a sub 0 through n, all of those are just numbers, so those aren't variables. And notice a single variable, right, one variable, I'm referring to the x here. So notice I don't have like an x and a y and a z, it's just straight up x. And I'd write it in a single kind of standard form, highest exponent all the way to lowest exponent, right? And if I asked you what the leading term was, you would say it would be this guy, whatever the leading term was there, right? If I asked for the leading coefficient, it would be that, just whatever the coefficient of the highest degree term was. If I asked what the degree of the polynomial was, it would be n, right? So nth degree polynomial, so it could be like a fourth degree polynomial, which we'd call, of course, a quartic. All sorts of stuff like that. A bunch of our former language still applies. So that's what a polynomial of one variable looks like. And then we're going to extend that to a polynomial function. All right, and you might recall that functions have exactly one output for every input. All right, we'd be able to have the notation kind of like this: f of x equals, and then it would be the a sub 0 x to the n plus a sub 1 x to the n minus 1 dot dot dot. It'd be that whole thing, except it's got an f of x in front of it, right? So basically, I can input stuff and I get outputs. And I said this is a function, so that means that graphically speaking, it would pass the vertical line test. All right, so it's never going to somehow loop back on itself. It's never going to do anything crazy. There'd be exactly one, output for every input. All that sort of good stuff applies. So let's actually talk about polynomial function real quick. Do a quick example of a specific function, and then we'll consider some generalized facts about the graphs of polynomial functions. So let's say I have the function f of x equals 2x cubed minus 5x plus 1. All right, so there's a polynomial function. It's a third degree. You've seen things kind of like that before when we had expressions but not functions. So let's say first thing I wanted to do was for part A, let's calculate what is f of 0. So what do you think that means? What does that mean to do when I'm evaluating? Yeah, plug a 0 in for all of the x's, right? So 2 times 0 to the third power minus 5 times 0 plus 1. 0 cubed is 0. Minus 5 times 0 is 0. It looks like this is just going to simplify to be 0 minus 0, which is 0, because they cancel out, of course. Funny. 0 minus 0 cancels out. It's hilarious, guys. Come on. Plus 1 is 1, right? So I get f of 0 equals 1, right? Graphically speaking, I could have written that as the ordered pair 0, comma 1. When the x was 0, the y was 1, right? Let's do, what if I wanted to calculate f of, let's say, negative 2? You could do 73 if you wanted, but that'd be a lot of work. But we could. Yeah. Yep. Just getting used to the idea of functions, right? I have an input and I get an output. Bam. So, when I'm evaluating these, you have to follow the order of operations very carefully. So when I do this, for instance, I can't multiply 2 and negative 2. I have to do the exponent here first, right, just to make sure. So negative 2 cubed, or all cubed, what's that going to be? Negative 8. Yeah, that's right. It actually keeps its minus sign because it's an odd degree. If it was an even degree, the negative would become positive. Negative 5 times negative 2 is positive 10, and then plus 1. 2 times negative 8 is negative 16, plus 10, plus 1. So let's see, that's negative 6 plus 1, or negative 5. Right, so that's f of negative 2. The output is negative 5 when I plugged in negative 2. To write that as an ordered pair, it would be negative 2 comma negative 5. Right, so the graphical side of that, if I wanted to point, that's what that would be. Actually, I just thought, rather than doing the third sample with the same function, I'm just going to make a bit of a friendlier function for us. Let's say I have, let's change the letter. Let's make it g of x. What? That's absurd. What? G instead of f? This guy's crazy. What if I've got, instead of 2, let's make it 3x squared minus... Man, why do I keep thinking of the same exact numbers? 8x plus 3. There we go. And let's say I want to, this time, figure out what is g of a plus 2. 3 times a plus 2 all squared, right? 8 times a plus 2. So I'm just going through and replacing the x's with a plus 2's, right? And then plus 3, yeah. And I just want to point out, g of a plus 2 does not mean g times a plus 2. It's I'm plugging a plus 2 into the function g, is what that means, right? So, to figure this out, let's simplify. I can't multiply here yet. I have to use the exponent. And you guys wouldn't dare think of distributing an exponent over a plus 2, right? No, you wouldn't. You never, ever would have done that. That's basically going to be this pattern here. A plus b all squared is equal to a squared plus 2ab plus b squared. But I know you guys already had that one memorized. You guys are awesome like that. So 3 times a squared plus 4a, when I calculate it all out, plus 2 squared is also 4. Minus, let's see, on this one, I actually can distribute, whoop, whoop, right? Negative 8a, and negative 8 times 2 is negative 16, and plus 3 is hanging out there. Keep on simplifying. Here we go. Now I can distribute this 3. So I'll have
Looks like a bird.
3a squared. All right. It's like a bird,
His face.
like a beak right
Yeah.
here.
Yeah.
All right. I see that. I see that. Mm-hmm. Minus 8a, and I think negative 16 and 3. I could simplify ahead of time here. That's going to be negative 13, if I'm not mistaken. So let's see. Combine like terms. Does 3a squared have any friends? No. So it's just plain old plumb ordinary 3a squared. Let's see. 12a has a friend. It's negative 8a.
So that's 4.
Yep, because remember when we're combining like terms, you combine the coefficients and then the variable remains the same. And then I've got 12 and negative 13 minus 1. So this is the value of g of a plus 2. All right, so it's kind of an unusual little thing, but sometimes it actually would make sense to plug a function into another function. Craziness, but it works. So that's some of the I guess quick application side of things. Let's talk about functions in general and their graphs. Let's see. Do I have enough room here? I'm going to go up to this side over here. Yep. Oh, craziness. Yikes. So let's talk about graphs of polynomial functions. All right. So we're going to look at 6 particular samples and then generalize some information about them. So the first thing I want us to consider is a constant function. Where's my mouse hiding? Right there. Bam. There we are. So constant function. All right. Would look something like this. F of x equals 2. Graphically speaking, does anyone know what a constant function looks like? What if that said y equals 2? What would that be? Yeah, it'd be a horizontal line, something like that, right? So that's what a constant function would look like. And this is degree 0 because I could have viewed this as an x to the 0th term if you really wanted to, but I don't know. Let's see, a linear function would be something like f of x equals 3/2 x minus 3 perhaps. So this is a first degree. And linear gets its name from the fact that it's kind of like a line, right? So this one would have had like a y-intercept of negative 3 and a slope of up 3 over 2. So it'd be kind of steeper than it was less steep, if that's a way I could describe it. And it looks something like that, right? Linear function. So constant functions are horizontal, they're always the same. Linear functions are changing their output depending on their input, and it's a first degree. Stuff like that. Let's see. I'm going to leave a little bit of space, and we'll talk about a quadratic function, which we are all masters of the quadratic function. So if I have a quadratic function, let's say I've got something to the effect of f of x equals x squared plus 2x minus 3. What would the graph of a quadratic function look like? A parabola. Exactly. Exactly. And this one looks something like this. And I don't actually really care where it lands right now. I'm just interested in the general behavior. Come in. No, they're afraid. It's okay. So, quadratic function, right? Looks something like that. What's the degree of a quadratic function? 2, right? Degree is 2. Bam. All right, now let's get crazy. What about a cubic function? I don't know if you guys have ever seen the graph of a cubic in your life. Yeah. So let's say I've got something like f of x equals x cubed minus 5x plus 2.
Don't you need an x squared?
Not necessarily. Like we've had quadratic functions that didn't have a linear term. So it's possible. So a cubic function, are you ready for this? Would look something like this. Whoa, it's kind of looking like a parabola. But no, what? It just switched things up on you. Craziness. I mean, it almost looks like, if I was to like kind of break it right here, that this is part of a parabola and this is part of a parabola. Almost. It actually doesn't necessarily hold the form, the same shape like that. It wouldn't have a down 1 over 1, down 3 over 1 slope thing going on. But I just want to point out, like, the kind of general curviness of it, you could almost think about kind of like that. And what's the degree of a cubic function? 3. It's a third degree function. We'll leave a little space. And let's talk about a quartic function.
This is gonna be
Crazy? All right. Hang on to your hats. F of x equals, what if I've got something like x to the 4th minus 3x squared minus 2x, no, 3x cubed, sorry, minus 2x squared plus 7x plus 1, how about? So what's the degree on this one? 4th degree. So notice I've been increasing in degree by 1 for each of these examples. Now, let's see. All right. Parabola was kind of this shape. Cubic was that shape. What's your theory on a quartic?
It's gonna like go up and then like down and then up and then back down. So yeah, like an M.
Like a letter M? Okay. In this case, it's going to be more of a W, but I'll give you credit for that theory. If it was an upside down one, it would have looked like an M. But yeah, you had the right idea. You knew that it was going to have that general form, right? Yeah.
No.
So that's what this would end up looking like for a quartic. And how about a quintic function, or a 5th degree polynomial? I think that's the first time we've used the word quintic. Maybe I might have mentioned it before. So what if I had something like this? F of x equals x to the 5th minus 5x cubed plus 4x. What's the degree of a quintic? 5, right?
It's gonna like, if it starts from up, it's gonna go like down, up, down, up, down. It'll be like,
Ready, here we go. What? 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 Craziness. Something like that.
it's like an M with one of its legs.
Yeah, sure. I like that. It's like an M with one of its legs broken. So let's see. So looking at these graphs, I want to analyze a couple things about them. Let's talk about x-intercepts. Should I just call them roots? Yeah, I'm going to call them roots for each of these.
That one doesn't make sense.
Roots. Let's see. Roots for the constant function, there's kind of two situations. It's either no x-intercepts
Or all of
or infinitely many of them. So that's kind of like just a weird case, right? If it landed exactly on the x-axis, it would just be all of them. How about roots for a linear function? What's the maximum number of times this could cross the x-axis?
it. One.
Just one time, right? Yeah. How about for a quadratic function?
1 or 2.
It could have
0, 1 or 2.
0, 1, or 2. Yeah. But at most 2, right? Because I mean, I can't somehow get a line to pass through it more than twice. Otherwise, it's not a line anymore. All right. What about for the cubic?
0, 3, 1, 0.
I agree 3's the max. Could I have had 2?
No. Yes. Yes.
What if I had a graph like this? What if it went and like ricocheted? Wouldn't that be 1 and 2? Okay, so 2 works. Does 1 work?
Yes.
What would 1 look like?
Move that other line
Yeah.
up a little bit.
If it was just like this kind of bend, it would have hit at one spot.
And then 0.
What would 0 look like?
Just in the quadrant. That's what they call it, right?
So it would look like this.
Yeah.
But the problem is this arrow here,
Okay.
I can't, yeah, I actually can't draw a cubic in a way that it doesn't have at least 1. And actually with that in mind, could I have had 0 for a linear function? Right, unless the line was horizontal, but if the line's horizontal, then it's a constant, right? Because the slope would have been 0, 0 times x. There is no linear term, so it's a constant function in that case. So it turns out for the linear function, I also wasn't able to have 0 roots. All right, how about for a quartic function for roots?
1. 4.
4 is the max, do we agree? 1, 2, 3, 4. Now, it doesn't have to be symmetric like this, all right? It's possible to have like this, you know, something
So
crazy.
that's 3.
So you can have 3.
2.
Could we have 2? Yeah, double ricochet. Bam. Bam, right? Double ricochet would be.
So let me say 1.
What would 1 look like? Single ricochet, and then like the other one maybe just goes off that way. And actually, wait, we could have had a 2 this way, where 1 deep part of the W, and then like, you know, so it didn't have to be a double ricochet. So we could have 1, and you're saying we could have 0 this time? Huh. So yeah, you're right. Because both of those arrows is what it's, yeah.
So if
Or it's actually even possible to have a letter M1 if it's an upside down quartic. So you could have 0. Interesting.
so they even degrees.
Ooh.
0.
Whoa, do you hear that theory he just surmised? Even degree. Is a constant function an even degree?
Yeah.
It's an x to the 0th. All right. And 0. All right. Odd degree? No. Even degree? Yep. Odd degree? No. Even degree? Yep. And you're okay. That's an interesting theory. Let's write that down. Let's see. Theory. Even degree polynomials. Polys can have no roots. Or 0 roots. All right, that's worth knowing. I like that. Let's analyze the roots for the quintic.
5.
All right, 5. Could I have 4?
Yes.
Sure. Could I have 3?
Yes.
Could I have 2?
Yes.
Could I have 1?
1. Yes.
That would be like this. Where, well, that was maybe more bends than I needed. And could I have 0? No. Why can't the odd degrees have 0?
Because they go in different directions.
Right? It has to do with the different directions, right? Like if I said I have some crazy odd degree function, right? And let's say it's got like, 37th power. You would tell me I know it has at least one x-intercept no matter what, and it has to do with the fact that the arrows are pointing in opposite directions, right? Like if you know you start on one side of the x-axis and you end on the other, and if I like didn't teleport, right, it had to cross it somewhere, right? Like it had to. It didn't like go around the planet the other way.
You can make that into like a camel.
Yeah, that doesn't work. Sure. Yeah, these are a little bit camel-ish. I like that. So similarly, we would say odd degree polys must have at least one root. Okay, I like that. And it's related to this is what's called end behavior of the function. We'll talk about that in a little bit. What about bends?
None.
Bends.
0.
All right, you guys know what I mean by bends? Like where the curve changes direction. So bends for a linear function or constant, I guess, is 0, right? It's just straight. It's always going the same direction. Quadratic function, it actually has to have one bend, right? And what was the name of the point that occurred at that bend? The vertex, right? And so what I'm referring to as a bend is where the graph changes direction, right? It was decreasing, and now it's increasing, right? 0, because it's just always increasing or always decreasing. It never changes. So let's see, how about for the cubic function? All right, it actually has at most 2 bends. It could have, it can have 0 bends, kind of. Let me show you an example of that. It could look like this, where it never actually stopped. Like, right, there's like something happened there. It was increasing at a slower rate, but it was still increasing, right? But it didn't actually have like a full change in direction. So it is kind of possible to have 0 as well. Just want to point that out. Quartic function, how many bends? 3 bends, right? And these aren't called vertices or anything. Those would be called, sometimes they're referred to as extrema, like the extreme values of the function, right? The peaks and valleys of it, sort of thing. Let's see, it's possible to have some other numbers, but at most 3 is kind of what occurs there. I guess fewest would be 1. Also just related to the end behavior. You could have that. And how about for the quintic? 1, 2, 3, 4.
I'm thinking all odd ones can have 0.
Yeah, I think so. And I think that
And the most they can have.
I think this could also have 2 or 0. But the one that the thing that I really want you to focus on is the maximum. Does anyone have a theory for the maximum number of bends?
It's 1 less than the degree.
Okay, so the maximum number of bends is 1 less than the degree.
It's not necessarily true.
No?
No, because the first one.
Yeah, the first one's kind of like a degenerate case where we're not that interested in it. It's like, meh.
Because the degree is 0 and 0 times 1 would be
Negative 1 bends. I like it. It's extremely straight. Like, it's got no bends at all. It's just like super, it's the most liniest line you could have. Okay, so that's good stuff. Maximum number of bends. Let's see. What was the other thing I wanted to talk about? How about end behavior?
I don't know what that means.
End behavior. Let's talk about the arrows. For a linear function, the end behavior was in opposite directions. For a quadratic function, they're heading in it came in from the positive side and goes out the positive side, right? Or could be negative negative, right? Let's see. For this one, the end behavior is opposite, same, and opposite. So even degree have end behavior in the same direction. And by default, odd degree have end behavior in opposite directions. All right. So let's see. Now I actually want to describe the end behavior real quick. This is the last thing we'll do. What time do we get out of here?
22 right now.
And we get out at 24? Good. We're good. We're good. Last example. Describe the end behavior. Look, I've only got like this much space to do it, so don't fret. It's not going to be long. Describe the end behavior. What if I have this function, f of x equals, let's start with a quadratic, just regular old one, x squared plus 2x minus 7. All right, so you guys would know that the end behavior is in the same direction, right? What way would this parabola open?
Up.
And how did you know that? Right, the leading coefficient is positive, right? It was a positive 1, so I knew it was up. It turns out, based on the leading coefficient, if I made this negative, the whole thing would be flipped, all right? So I just want to point that out. All of these can be flipped upside down by their leading coefficient. So the end behavior, this is how we'd write that language. Let me describe this left side here. What is happening to the y values? Y values, as we get further, are going positive, right? So I would say f of x approaches positive at infinity as x approaches, and x is, it's going further to the left here as the y is going up.
I have a question.
1 minute. As x approaches negative infinity. So basically I'm saying this goes up as we were going to the left. And similarly for here, I'm going to say f of x goes to positive infinity as x goes to positive infinity. Right? So basically I'm describing over here that as y was increasing as x was increasing. All right? So this is just the mathy way to describe end behavior. Okay? So, thanks for watching, internet friends. I know it was a long video, but bye-bye.